Hello, I'm Carlos Rosas and this is the Sierra's channel. Okay, now we're gonna finish up with the exercise for a circle circumscribed to triangle. The product of the lengths of any two of the sides of a triangle is equal to the product of the diameter of the circle and the altitude traced to the third side. And I'm going to finish the case B, which is the acute angle triangle case. Okay, so let's summarize the equations we had already obtained in the other two previous videos. We had one relationship that was theta 1 plus theta 2 equals alpha plus beta. The other relation was theta 1 minus theta 2 equals alpha minus beta. If we add these two, we have 2 theta 1 equals 2 alpha, and therefore we have theta 1 equals alpha. If we subtract these two, we have 2 theta 2 equals 2 beta, or theta 2 equals beta. Okay, as for the trigonometric functions of the angles, we have that sine of theta 1 equals a over d, sine of theta 2 equals b over d, which can be seen here in the figure. Sine of theta 1 equals a over diameter d of the circle, which is g prime. And sine of theta 2 equals b over d, which is the diameter of the circle. That d has to be distinguished from this other d, which is a point. Unless I specify to the contrary, then the d for this video will be the d corresponding to the diameter, that is the length of g prime. Okay, so we have then that sine of alpha equals hc over b, and is also equal to hb over c. Sine of alpha equals hb sine of alpha equals hb over c. Is this side over this side, and is also equal to hc this side over b, which is this side. hb over c and hc over b. Okay, we also have then that sine of beta equals hc over a equals ha over c. Sine of beta equals hc over a. Sine of beta equals ha over c. hc over a and ha over c, as we have here. Okay, so with those relations, then we have that since theta 1 equals alpha, that means that sine of theta 1 equals sine of alpha, which means that hc over b equals hb over c equals a over d. We also have then that sine of theta 2 equals beta, so then we have that sine of theta 2 equals sine of beta. So that means that HC over A equals HA over C equals B over D. Okay, so all we have to do now is send the numbers of the denominators to multiply on the other side. And then we have that taking, for example, these two, this one, and this one. We have AB equals HC over HC times D, and this one, with this one we have AC equals HB times D. Multiplying using this one and this one, we have again AB equals HC times D. And using this one, we have that BC equals HA times D. So we have sides A and B multiplying each other, and we have the height of the third side, which is C, times the diameter. The same here. And here we have A times C, the third side then being B, such that the height traced to B, which is HB, is multiplying the diameter. And the product of B and C, with the third side being A, will be equal to the height traced to that side, HA, times the diameter of the circle. Okay, so there we have proven or completed the proof for the case of the acute angle triangle. Now we can go to the case of the obtuse angle triangle. Now the obtuse angle triangle is simply triangle BGA. This is not a very general diagram. I suggest that when you draw it yourselves, move the point B up here or down here a bit, or do that with point A, such that if you move point B and point A at the same in the same diagram, do move them in opposite directions. The analogs to right angles BGG prime and AGG prime for the obtuse angle triangle are the same, BGG prime and AGG prime. GG prime is the diameter, and the analogs for the right angle triangles that were used here, and for the case of, for example, the sine of beta, or sine of beta in this case would be a right angle triangle BDA, where D is outside the triangle. Here it's inside the acute angle triangle. Here D is outside the obtuse angle triangle. The other triangle, for example, used here was for sine of beta was a triangle BGF. That would be BGF here. So we have BDA and BGF. For sine of beta, we had triangles ABE. Here would be ABE, with E being outside the obtuse angle triangle BGA, while in the acute angle triangle case it was inside the acute angle triangle BGA. For the obtuse angle triangle, it's outside BGA. So we have BEA and triangle BEA, and we also have triangle AGF, which would correspond to this triangle AGF here. Now we used, to obtain the relations, the angles, the acute angle triangle directly. Here we do the same. We obtain the alpha plus beta plus gamma equals pi. And BCA is the same. We use that same triangle BCA for the obtuse angle triangle. So here we have that sine of alpha equals HB over C, which is the same relation we had for the acute angle triangle case. So we're going to simply write down the relations, but that we will do in our next video.